This is lesson number 43, part 2, beta decays. I'm assuming that you've already had a look at part 1, and if you haven't, I would suggest you look there first because we can kind of lean on some of the things that we learned about alpha decays to be able to say some things about beta decays as well. So I'd say watch that one first and then come back and watch this one. But the purpose of this video is to look very specifically at beta decays, and that's all we're going to be looking at. Now, beta decays have their own very specific set of properties. First of all, their ability to penetrate matter is considerably more than what the alpha particles were, because alpha particles, remember, are big, heavy, fat helium nuclei. Whereas beta particles, well, they must be a lot smaller because they can actually get through things relatively easily until we start getting into things like using metals to block them. So if I had a source of beta radiation in front of me, I could put maybe a couple sheets of aluminum foil on top of it, like the kind you buy at Safeway, and it will block the beta radiation. But it's got to be something pretty thick like that. And then we get our hint as to what it really must be, because we remember that beta particles are deflected as negative charges in magnetic fields. That's because they are really the most common negative particle that exists. They are electrons. So that does mean that they are not as strong a form of ionizing radiation as alpha particles were. Alpha were a double positive elementary charge, but here an electron is just a single elementary charge that happens to be negative. The issue, though, is I don't have to ingest the source of a beta radiation emitter to be able to get the beta radiation, because it will actually, the beta particles will penetrate about 1 centimeter into my body, which means they're right there with living tissue, living cells. So that is a significant risk we have to realize we have to guard ourselves against when we're dealing with beta radiation. And maybe use some form of barrier that is metal to be able to prevent it from reaching us. Now, the other kooky part is beta decays actually come in 2 different types. The first one is called beta negative, and it's really the one that we've been talking about when I've been saying, hey, it's really an electron and it acts as a negative particle in a magnetic field because of that. This is the classic beta radiation. This is what Rutherford himself observed. And that's because this form of beta radiation is relatively common. Whereas, guess what? Beta positive, the other kind, is much, much more rare. And we're going to see when we get into the specifics of beta positive decays why. But they are deflected as positive particles in a magnetic field because they are single elementary positive charges. I don't want to say too much more, though, until we actually get to talking about them, because it is kind of weird. Anyways, to discuss beta negative, what we really have to understand is what the beta negative particle is. Because I already said it's an electron, but that gives us an issue, because I said it's coming out of the nucleus. It's part of a radioactive decay that happens in the nucleus. You might recall way back at the beginning of talking about properties of nucleons, we did mention that the mass of a neutron is ever so slightly heavier than the mass of a proton. Now, this is a bit of an oversimplification of things, but yeah, a neutron is basically a proton and an electron stuck together. Because if you do look at those A and Z values that are written there, everything balances out. A neutron being made up of a proton and an electron, that beta negative particle is an electron. It actually makes sense. And just so you understand when I'm looking at this, the reason the beta negative has a Z value of -1 is because its opposite charge of a proton, it's a negative, and it has a value of 0 because it is not a nucleon. It does not belong in the nucleus. So as soon as a neutron decays into a proton and a beta negative particle, the beta negative particle ejects immediately from the nucleus because it doesn't belong there. It's not a nucleon. So let's look at writing out a basic beta negative decay. I tell you that calcium-46 goes through beta negative decays. So I go to my periodic table and I find calcium, its atomic number 20. I write down its A and Z values. I know that for certain one of the products that has to come out is the beta negative particle itself. So put that down first. And then I do conservation of nucleons on the top, and I do conservation of charge on the bottom. So far, I don't have any of the nucleons, and there should be 46. So I know whatever my daughter nucleus will be, will have 46 nucleons. That's because even though we've ejected an electron, because a neutron turned into a proton, the total number of nucleons stayed the same. Although the number of protons jumped up by 1. Hey, and I see that when I look at the Z values. I start with a Z value of 20. And so far I've only seen -1. Yeah, because the opposite of a proton came shooting out. That means that I must be looking at scandium, which has an A value of 46 and a Z value of 21, because that way, if I look at my conservation of nucleons on the top and conservation of charge on the bottom, everything adds up. The left side and the right side are the same. Yay! But there is one thing a little bit odd here, because another particle does come shooting out. And we write it sort of like a handwritten italicized letter V with a little bar above it. And that last particle has to be there, because when physicists were first examining the beta negative particle decays, what they realized is the beta negative particles were coming out moving too slow. They weren't doing conservation of energy or momentum for us. So what they realized is there must be another little teeny tiny particle that's coming out, and it's going to have almost no mass, but it's moving wicked fast and it has no charge. That's why it's so hard for us to detect it and notice it. So the Italian physicists that were doing this said, hey, it's not just a neutron, it's a baby neutron, because it's so tiny but neutral. So baby, bambino, neutron, neutrino. Now, very specifically, we're talking about something called the antineutrino here, because during beta negative decays, it's not just a neutrino, it's an antineutrino that comes out. The bar written above it is what shows it as an antineutrino. The way that I used to remember this when I was a student is that during beta negative decays, when I wrote that -1 on the beta negative particle, I kind of saw that as being the bar that's written above the neutrino to make it an antineutrino. More on antineutrinos when we get to antimatter in a later lesson. For now, you just need to know that they have to be there. Then there's beta positive decays. One thing I'll tell you is, like when you're doing something in a study in physics like nuclear physics, as soon as you think you understand things, it'll throw you a curveball. So here, what we're seeing is a proton decaying into a neutron and 2 other particles, but the proton's lighter. Don't worry about it. If we use conservation of mass energy, that just means that energy somehow is coming into this system to allow additional mass to form. The important part, though, is the proton creates a neutron, the beta positive particle, and a neutrino. There's no bar above it, so it's a neutrino, not an antineutrino. The kooky thing about that beta positive particle is that it is the opposite of an electron. And no, I don't mean proton. I mean an opposite electron. It has exactly the same mass as an electron, but it has a positive charge. It's an anti-electron. It's the antimatter version of an electron. That's why we sometimes call it, though, also a positron, because it's positive, but like an electron. So the beta positive particle is a positron, an anti-electron, the antimatter version of an electron. It has positive charge, but all the mass of an electron. Crazy, I know. Now, what I'd also suggest you do is write this out and try to put in the A and Z values to kind of show yourself that we're not violating anything here. Then we move on to writing out a beta positive decay. I tell you that potassium-40 is known to go through beta positive decays. This probably doesn't happen very often because they are comparatively a rare decay, but they will happen. So we could just observe this long enough and see it happen. I ask you to write out the decay. So we start it just like we would any decay. We write out our parent nucleus, potassium-40, and I looked up on the periodic table. It has a Z value of 19. I know that one of the things I have to produce is the beta positive particle, so I put it down with its A and Z values. That means argon is my daughter nucleus, because that way 0 plus 40 equals 40, 1 plus 18 equals 19. I have conservation of nucleons and charge on the left and right. But don't forget, you're going to get this wrong if you forget to add on that neutrino at the end. It's a very common thing, like on a diploma, they'll show a reaction that looks, or decay that looks very much like this. There'll be 4 of them, and 3 of them will have little mistakes, like maybe the neutrino has a bar over top, or it's just not there at all. And they just want to make sure that you can actually pick out the one that's actually written completely correctly. Now, the last thing we're going to mention is something called inverse beta decays, otherwise known as electron capture. This is technically not a beta negative or beta positive decay, but they're so similar. I think they're kind of worth mentioning here. And honestly, if this was going to appear like on a diploma, they'd give you like an information box and they'd be telling you about this, but then they'd want you to still be able to write it out. But this is also a great example of how we can show you something that's a decay that you haven't studied before, and it follows all the rules, and as long as you write it out following the rules, you'll be okay. So the crazy thing that happens here is a proton-rich nucleus absorbs an electron from one of its inner energy levels. Now that sounds kind of weird, but think about it. This is basically a proton pulling in an electron so that it can become a neutron. That's effectively what's happening. So in that process, the proton sucks in the electron. We'd have to do our conservation of nucleons and charge here. I get a neutron as my product, and just the way it happens to work out, a neutrino is also produced. So if I said to you that rubidium-83 goes through these very rare electron captures, and I wanted you to write out the decay equation for it, it would look quite different from the other ones. Because I start with the rubidium-83, and yep, I had to look up on the periodic table that its atomic number is 37, and then I add the electron to it on the reactant side, if you want to think of it that way. And it's because unlike the other decays where something just starts on its own and spontaneously releases particles, here we are absorbing an electron at the start. So I still do my conservation of nucleons and everything like that. So 83 plus 0 still equals 83. 37 plus negative 1 equals 36. The only thing that could be with atomic number 36 is krypton. And then don't forget to throw that little neutrino on the end there. That is it for beta decays, the second part in this series that looks at lesson number 43. Make sure that you also check out the third part, which will be gamma decays. Thank you and good luck.